And let's start with an introduction. Correlation is a quantity that describes how strongly two variables are linearly associated. Yeah, we are talking about linear association, first of all. Usually you use the letters R, capital R or non-capital R, or the Greek letter Rho. Usually R is used for the Latin letters are used for samples and the Greek letters are for the population. So, the magnitude, the absolute value of R tells us how strong the correlation is. So here are three sample plots with a strong correlation, a not so strong correlation, and a weak correlation. And one way to actually interpret this means a strong correlation means if I increase X, I also increase Y. This means a strong correlation. Yeah? If X grows, Y also grows. If it's +1, if it's -1, it's the opposite way. Or in other words, pick a random point here, this one, and if I go to the right from this point, I will mostly find data points that have higher Y values. That's a positive, strong correlation. If we have a weak correlation, like here, if I go to the right, I will find points that have higher Y values and lower Y values, but more that have a higher Y value. And if I have a zero correlation, and I move from this point or any other point to the right, yeah, I will have about equal number of points above and below. The R value is always between plus and -1. And minus means anti-correlation, so like here on the bottom right. That's the direction of the association, and positive is an increase here. So there's a positive delta X means positive delta Y. Yeah.
Does the correlation have to be linear? Could it be like quadratic or even periodic in some way?
The way how the correlation coefficient is computed, if you have some sample, doesn't know about functional dependency. It just measures how does delta X and delta Y correlate, and that's a linear question. Yeah? If it's periodic, if you imagine a sine, it depends where you stop, whether it's a linear thing or if it's zero correlation or if it's negative, so on. Correlation coefficient can tell us only about linear association. Yeah? We will see this later. Let's say all the points are sitting along one line, then this is a perfect correlation. Yeah? Which, in other words, I can predict if I start here and say, let's go delta X 1 to the right, I can predict where the next data point is. Namely, I can compute delta Y. Okay, so we will see later that the correlation coefficient is apparently unitless. Yeah? And it's not affected by linear transformations of your data. So if you recenter your data, if you scale it somehow, if you make unit conversions, it doesn't matter. Yeah, this cancels out. Or if you switch the x and y axis, which is a rotation on the diagonal, the correlation remains the same. Yeah. even though, of course, the plot of data points is switched, but the result of the correlation coefficient is the same. And, very importantly, the correlation coefficient is extremely sensitive to outliers. Let's say I have this data, which has this correlation coefficient, and if I add one data point here, the correlation coefficient drops by 30%. Yeah? So, given that, what would be your guess on what is the correlation coefficient from this plot here?
So it should be negative because its tendency is negative.
Exactly. So we have three negative numbers, minus 0.1, 1.5.
That can't be because we are limiting.
Okay, it needs to be between minus 1 and plus 1. This or this one, which one should it be? The number 3?
Yeah.
And number 3 is basically 0. 0 means no correlation. Yeah, so that doesn't look not correlated. Seems okay. It's somewhat suggestive because I printed in here these triangles and the red line to guide your eye. Yeah, but nevertheless, there is a clear dropping trend. Yeah, that's how a correlation of minus 0.7 looks in data points. We would always say this is actually pretty close to minus 1. But in scatter, it's still significant. So, yeah. In other words, if you have an 0.8 correlation, numerically this sounds good, but actually it's quite a scatter. Yeah? Okay. Let's see what comes next. Okay. The point is, we are always looking for correlations, if we want or not. Your whole brain is trained and specialized to find correlations. That's all it does, 24 hours a day. And it will find something. Yeah? If you look, wherever you look, your brain sees faces. Yeah, you need two dots and a line, and it's a face. Yeah, that's how our neural network works. And with correlation, it's the same. We see something, but let's take an example. That's a plot from Sandage, very famous Sandage paper from 1972. Sandage was heading one of the two fractions between the 50s and 70s who were trying to determine the Hubble constant. There was a big fight over 30 years what the correct Hubble constant is. One fraction was aiming towards 50 kilometers per second per megaparsec, and the other to 100. Yeah, it was for 30-40 years heavy fight. They all had data, and from their data they came to either 50 or either 100. The modern value is 72. Of course, it's in the middle. Yeah? But this was one of the plot of 3CR radioluminosities. 3CR is a catalog of radio brightnesses of galaxies. As a function of distance. That's here in some arbitrary co-moving distance in magnitude. So some arcane unit, but it's distance. Yeah? Far away, close. And that's brightness, so bright and faint. And what we see here, each dot is a galaxy. And immediately your eye tells you there's a correlation. And correlation saying remote galaxies are brighter. The universe was brighter in earlier times. Yeah, that's some significant claim. Okay, so the problems with this plot are, first of all, the line that's plotted here is the detection limit of the detector. The detection limit means we cannot observe anything below this line. Just because the signal is too weak. If we go further away, brightnesses of an object decrease with distance squared. Yeah, so that means this line has to increase with distance, because our detection limit is some absolute numbers. We can detect, I don't know, if we have at least 10 photons per second, that's a detection. Okay? And for very distant objects, all the photons that are emitted are distributed across a much larger sphere, a sphere with diameter of many megaparsecs. So, yeah, the photon density on every square centimeter on this sphere is much, much smaller. So it needs to be brighter for us to be detectable. That's why this detection limit goes up. Okay? So we cannot observe anything. Maybe there are thousands of galaxies here, just we can't detect them. They are too faint. Good. But what about these? At least here, we don't see anything, and these are detectable, right? Why, if we don't see something, there needs to be some thing here. And again, no. If you look at a given distance, at the luminosity distribution of galaxies that are all at the same distance, then what you find is there is some power law going on. We have many, many faint galaxies and very few bright galaxies. Yeah, that's the power law. And in this plot, which is an exponential a log-log plot, that means many, many faint objects means many objects here and very few objects when we go in this direction. Yeah? So, of course, all the points are clustering here, because that's where our power law of the luminosity function has a high probability to produce a galaxy in our sample. Yeah? If we would just observe longer and longer or take larger samples, we would start, this clustering would widen and we would start to observe things here. We need to make the volume that we are observing larger. Yeah? To have a chance to find one of the rare, very bright objects that are very seldom in our power law luminosity function. So here it's a combination of underlying distribution with our detector limitations that create a correlation, an apparent correlation. Yeah.